For the first topic for our discussion in chapter 2 is laws of logic. There are 12 laws in this topic, and these are the example. We have double negation law, De Morgan's law, commutative law, associative law, distributive law, idempotent law, identity law, inverse law, and more. For the first example in this topic, we have P and Q as propositions. The propositions P or Q, denoted by P, V, Q, is the proposition that is false when both P and Q are false and true otherwise. P, V, Q is called the disjunction of P and Q. Let's look at the question. We have P, V, Q in bracket apostrophe disjunction in bracket P, V, Q prime apostrophe. For the first step, change the symbol disjunction P and Q with the symbol conjunction in the bracket, and at the same time P and Q will have the apostrophe. The changes in symbol is what we have in De Morgan's law. The next step, we have the double complement in Q, so we will get only Q. Then we will have 2P prime, and simplify, we will get P prime in conjunction in bracket Q prime and Q. In this step, we use distributive law, so simplify Q prime and Q, we will get P prime conjunction U, which is inverse law. Then the last answer, we will get P prime, which is identity law. Next, we move to the second example. The question wants us to determine whether the proposition is logically implies and logically equivalent to P, V, Q, and P respectively. In this case, we must use the truth table. For the question 1 Roman, P logically implies P, V, Q. For the first step, draw a table with 3 columns and label each column as P, Q, and P, V, Q. Then fill the table in P and Q with the probability true and true, true false, and false false. To get P, V, Q, we must refer to the formula in the truth table for disjunction. For example, for both P and Q are true, we will get P, V, Q also true. Same goes to if P true, Q false, or P false and Q true. We will get both true for P, V, Q. For the last row, when both P and Q got false, the disjunction of P and Q will also false. Next, for the example 2 Roman, the question asks whether P in conjunction Q is logically equivalent to P. Same with the first question. Draw a table with 3 columns and put the P, Q, and P conjunction Q in each column. Then fill the table in P and Q with the probability true true, true false, and false false. To get the P conjunction Q, we must refer to the formula in the truth table for conjunction. For example, for both P and Q are true, the conjunction between P and Q will be true. For P true and Q false, or P false, Q true, the conjunction between P and Q will be false. For the last one, when both P and Q are false, the conjunction between P and Q are also false.
Argument. Argument is a list of given statements called premise and followed by the final statement called conclusion. As we can see at the example, P1, P2, P3, and Q. P is for premise and Q is for conclusion. All the premise can be called as a hypothesis. If it is on the premise true, then the conclusion is also true. It is a tautology. Next, rule of inference. We have 8 rules of inference. First, we have modus ponens. Next, we have rule of disjunctive syllogism, rule of conjunction, rule of conjunctive simplification, law of syllogism, rule of disjunctive amplification, modus tollens, and finally is rule of contradiction. So let's answer the question. Consider the following argument. If Eric composed music in the afternoon, then he practiced in the evening. If Eric composed music in the afternoon and practiced in the evening, then Henry or Amber cleans the house. Henry or Amber cleans the house. If Jason wins the music competition, then Eric composed music in the afternoon and John plays basketball. Amber did not clean the house. Jason won the music competition, therefore Harry cleans the house. First question is declare of the primitive proposition in the argument above using the variable P, Q, R, S, T, and U. First, we can declare P as Eric composed music in the afternoon. Q, Eric practiced in the evening. R, Henry cleans the house. S, Amber cleans the house. T, Jackson wins the music competition. U, Jones play basketball. Second question is write the premise of the argument using the P, Q, R, S, T, and U. So we can answer P implies Q, P and Q implies R or S, T implies P and U, negation S, T and the conclusion is R. The third question is prove the validity of arguments using the rule of inference. Actually, this question can be proved by using the truth table or law of logic, but this question asks us to use the rule of inference. First, we must copy all the premise that we write in the question 2. After that, we can use modus ponens at line 3 and 5 and we get P and U. Then, we use the rule of conjunctive simplification at line 6 and we get P. To get Q at line 8, we must use modus ponens at line 1 and 7. After we get Q at line 8, we can combine P and Q using the rule of conjunction and we get P and Q at line 9. Last but not least, we must apply modus ponens again at line 2 and 9 to get R or S. Lastly, to know this argument is valid, we use the rule of disjunctive syllogism and we get R. To answer question 3, I use modus ponens. For example, when we have two premises, which is the first one is P implies Q and the second one is P and the conclusion is we get Q. The second one is rule of disjunctive syllogism. For example, at the first one we have P and Q and the second one is negation P and the conclusion we get is Q, rule of conjunction. For example, we have premise P and premise Q. We can combine them using N and what we get in the conclusion is P and Q. The last one is the rule of conjunctive simplification. For example, when we have premise with N, which is at the example we have P and Q, we can select one of these, which is we can choose P or choose Q.
Assalamualaikum. In this part, I will present to you all about quantifiers. What is the quantifiers? Quantifiers are words that refer to quantities such as some or all. It tells for how many elements a given predicate is true. There are two types of quantifiers. The first type is universal quantifiers and the second type is existential quantifiers. The symbol of universal quantifiers means for all and every. Meanwhile, the symbol of existential quantifiers means there exists some and at least. How do we know if the statement is true or false? If the statement is for all x px, it will be true when px is true for every x. Meanwhile, the statement will be false if there is an x for which px is false. If the statement is there exists x px, it will be true when there is one x for which px is true. Meanwhile, when false, it is because of px is false for every x. Let's see for the example 1 and 2 below for existential quantifiers. Number 1, px is x greater than 3 and the universe is real number. Let's say the question asks is there some value of x for which px is true. So the answer is yes, px is true because when we pick an example x equal to 4, then 4 is greater than 3. So this is a true statement. Number 2, there exists x equal to x plus 1 and the universe is the real number. When we bring x to the right and 1 to the left, we will get 1 equal to x minus x and x minus x will become 0. So 0 equal to 1 is false because no x satisfies x equal to x plus 1. Example 3 and 4 is for universal quantifiers. Let's see the example 3 first. Px is x squared greater than and equal to 0 and the universe is all real number. So the answer is for all x px is true. It is because all values of x is satisfied with px. Number 4, qx is x plus 1 less than x and the universe is all integers. So the answer is for all x qx is false. It is because when counted example x equal to 1, then 1 plus 1 less than 1 is wrong because 2 should be greater than 1. In this part, I will explain about translating word statement into logical expression. Before that, we must take note that we have to describe specific domain first when doing translating word statement into logical expression. Here is the example for existential quantifiers. Some student in this class has a partner. First step, we have to determine which px. Px is x has a partner. Second step, determine the universe. Universe is all student in this class. And then, write the simple notation of the statement as there exists x px. Third step, determine the specific domain. As x is a student in this class. Lastly, write it into logical expression as there exists x open bracket, as x and px close bracket. Make sure declare the specific domain first after there exists x. Here is an example of universal quantifiers. Every student in this class has a partner. The steps are same like existential quantifiers that I have explained just now. Px is x has a partner. The universe is all student in this class. And the simple notation of the statement is for all x px. The specific domain is x is a student in this class. So write them into logical expression. For all x open bracket as x implies px close bracket. The difference between existential quantifiers with universal quantifiers is after specific domain for existential quantifiers is n, while universal quantifiers is implies. For this part, I will explain about negation of quantified statement. For example 1, if there is negation out of the bracket, take it inside to the bracket and change the symbol of quantifiers. For example, if for all, it will be there as is and vice versa. After that, if it has double negation, the negation will be removed. So the answer will be there as is x px. For example number 2 is also same like example 1. Just change the symbol of quantifiers. For example 3, if it has implies, change the implication sign to the disjunction sign and add negation before of px. And don't forget to change the quantifier symbol. If has negation out of the bracket, take it inside and split the sign of disjunction to the conjunction. So the answer would be there exists x, open bracket px and negation qx, close bracket. Nested quantifier. Nested quantifiers are quantifiers that occur within the scope of the other quantifiers. If the statement is for all x for all y psy, logically equivalence for all y for all x psy, it's true when psy is true for all every pair sy. Meanwhile, it's false when there is a pair sy such that psy is false. If the statement is there exists x, there exists y psy, logically equivalence there exists y, there exists x psy, is true when there is a pair sy such that psy is true. Meanwhile, it's false when psy is false for every pair psy. If the statement is for all x, there exists y psy, is true when for every x there is a y such that psy is true. Meanwhile, it's false when there is an x such that psy is false for every y. If the statement is there exists x for all y psy, is true when there is an x for which psy is true for every y. Is false when for every x there is a y such that psy is false. Let's do some questions. Question A asks to negate the following statement. The statement given is there exists r for all s, r cubed plus s cubed less than 0. See at the solution, put negation in front of the statement and the answer will be for all r, there exists s, r cubed plus s cubed greater than and equal to 0. Question B, determine the true value of each of the statement with the indicate universal set. Justify your answer by giving example or counterexample. Solution for question 1, for all x there exists y, x squared less than y with universal set n, is false. If counterexample x equal to 2, y equal to 1, therefore 2 squared less than y, so this statement is false. Solution for question 2, for all x there exists y, x plus y equal to 0 with universal set z positive is true when example y equal to negative 1. Solution for question 3, there exists x, there exists y, x squared plus y squared equal to 13 with universal set z is true when example x equal to 2 and y equal to negative 3. Lastly, solution for question 4, for all x there exists y, x y equal to 1 is false because when counterexample x equal to 0, there is no y such that 0 times y equal to 1.
I will explain how to prove using the choose method. First option is we have to clarify A for set S, which is y elements to real number equal to y squared plus 2y minus 15 less than or equal to 0, while set T, y elements to real number equal to negative 5 less than or equal to y less than or equal to 3. Then we have to clarify B for T subset S, B1 which is for all S elements in set T and S also elements in set S. B1 which is choose A for elements in set T, B2 A elements in set S, A2 which is negative 5 less than or equal to A less than or equal to 3. For A3, we will get A more than or equal to negative 5 and A less than or equal to 3. A4, A plus 5 more than or equal to 0 and A minus 3 less than or equal to 0. A5, which is A plus 5 multiplied with A minus 3 less than or equal to 0. We will get A6, the equation is A squared plus 2A minus 15 less than or equal to 0. And lastly, we will get A7, which is A elements to S. And then B2 is proven.
The construction method. This method is used when the conclusion involves an existential quantifier. This method can be used if the conclusion B is in the form of there is an object with a certain property such that something happens. Let's look at an example. Use the construction method to prove that if m and n are rational and n is not equal to 0, then m over n is rational. Your answer should have an analysis of the proof only. First, we need to identify a hypothesis and conclusion. A represented as a hypothesis and B represented as conclusion. A is m and n are rational and n is not equal to 0. B is m over n is rational. B1, let's say m over n is equal to r over s. R and s is an element of integers. S is not equal to 0. A1, assume that m is a over b. A, b, c, d is an element of integers and n is c over d. CBD is not equal to 0. A2, M over N equal to A over B divided by C over D. A over B multiply with D over C. M over N equal to AD over BC, and let AD is G, BC is H. G and H is an element of integers. H is not equal to 0. A3, M over N is G over H. G and H is an element of integers. H is not equal to 0.